Section 430.63 takes precedence over Section 215.3 when determining the overcurrent protection device size for a feeder load. This feeder load is composed of lighting which constitutes a continuous load, receptacles which are non-continuous loads, and motors such as grinders and air compressors. Section 430.63 mandates that the overcurrent protection device be sized to accommodate the sum of the continuous loads, the non-continuous loads, and the locked-rotor current of the largest motor. The rationale behind this is that a motor's locked-rotor current significantly exceeds its normal running current. The overcurrent protection device must be capable of handling this inrush current without tripping unnecessarily. Section 215.3, conversely, only stipulates that the overcurrent protection device be sized to carry the sum of the continuous loads and the non-continuous loads. This approach would be inadequate in safeguarding the circuit against the motor's locked-rotor current. Consequently, Section 430.63 is the prevailing guideline in this specific scenario. Let's delve deeper into the specific requirements and considerations for each component of the feeder load. Firstly, the continuous lighting load needs to be calculated. Continuous loads are defined as loads that operate for 3 hours or more continuously. For lighting, this usually means general illumination in commercial or industrial settings. The total wattage of the continuous lighting is determined and then divided by the system voltage to find the current. This current is then multiplied by 1.25 or 125% as required by the National Electrical Code, or NEC, to account for the continuous nature of the load. This adjusted current value is a crucial component in the overall feeder load calculation. Secondly, the non-continuous receptacle load requires determination. Receptacles are generally considered non-continuous loads because their usage is intermittent and unpredictable. To calculate the receptacle load, the NEC permits the use of demand factors, especially in commercial or industrial settings where there are many receptacles. Demand factors allow for a reduction in the calculated load based on the assumption that not all receptacles will be in use simultaneously at their maximum capacity. The specific demand factors to be applied can be found in Article 220 of the NEC. The calculated receptacle load, after applying any applicable demand factors, contributes to the overall feeder load. Thirdly, the motor load, which is the most complex component, demands careful consideration. Motors, such as those found in grinders and air compressors, have unique characteristics that influence feeder sizing. Section 430 of the NEC provides detailed guidance on motor circuit and feeder protection. The first step is to identify the largest motor in the group. The full load current, or FLC, of this motor is obtained from NEC tables or the motor nameplate. The locked-rotor current of the largest motor is then considered. This value is significantly higher than the full load current and represents the current drawn by the motor when it initially starts. Section 430.63 specifically requires that the overcurrent protection device be sized to handle this locked-rotor current. The full load currents of all other motors in the group are then added to the locked-rotor current of the largest motor. This sum represents the total motor load for the feeder. The overcurrent protection device must be capable of withstanding the inrush current of the largest motor while also protecting the feeder conductors from overload. Now, let's consider how these three components are combined to determine the appropriate overcurrent protection device size. Section 430.63 dictates the following process. Firstly, calculate the continuous lighting load by multiplying the total lighting load by 1.25. Secondly, determine the non-continuous receptacle load, applying any appropriate demand factors. Thirdly, identify the largest motor and its locked-rotor current, along with the full load currents of all other motors. Fourthly, sum the continuous lighting load, the non-continuous receptacle load, and the locked-rotor current of the largest motor, plus the full load currents of the other motors. Fifthly, select an overcurrent protection device with a rating that is equal to or greater than the calculated sum. This ensures that the overcurrent protection device can handle the inrush current of the largest motor without tripping while still providing overload protection for the feeder conductors. It is essential to consult the specific tables and requirements in the NEC for accurate calculations and proper selection of overcurrent protection devices. Now, let's discuss the implications of using Section 215.3 instead of Section 430.63 in this scenario. Section 215.3 focuses on the continuous and non-continuous loads but does not explicitly address the locked-rotor current of motors. If the overcurrent protection device were sized solely based on Section 215.3, it would likely be too small to handle the inrush current of the largest motor. This could result in nuisance tripping, which disrupts operations and can potentially damage equipment. Furthermore, an undersized overcurrent protection device may not adequately protect the feeder conductors from overload conditions, increasing the risk of fire or other electrical hazards. Therefore, Section 430.63 takes precedence because it provides a more comprehensive approach to overcurrent protection in scenarios where motor loads are present. It accounts for the unique characteristics of motors and ensures that the overcurrent protection device is appropriately sized to handle both normal operating conditions and transient events like motor starting. Now let's explore the different types of overcurrent protection devices that can be used in this application. Firstly, fuses. Fuses are single-use devices that interrupt the circuit when an overcurrent condition occurs. They are available in various types, including time delay fuses, which can withstand short-duration overloads without tripping, and fast-acting fuses, which provide more rapid protection against short circuits. The type of fuse selected should be appropriate for the specific application and the characteristics of the load. Secondly, circuit breakers, which are reusable devices that interrupt the circuit when an overcurrent condition occurs. They can be reset manually after tripping, making them a convenient alternative to fuses. Circuit breakers are also available in various types, including thermal magnetic breakers, which respond to both thermal overloads and magnetic short circuits, and electronic trip breakers, which offer more sophisticated protection features and adjustable trip settings. The selection of a circuit breaker should be based on the specific requirements of the circuit and the desired level of protection. It is also essential to consider the interrupting rating of the overcurrent protection device. The interrupting rating is the maximum fault current that the device can safely interrupt without failing. The interrupting rating must be greater than the available fault current at the point of installation. Available fault current studies can be performed to determine the potential fault current levels. Using an overcurrent protection device with an inadequate interrupting rating can result in catastrophic failure and pose a significant safety hazard. In summary, when sizing the overcurrent protection device for a feeder load that includes continuous lighting, non-continuous receptacles, and motors, Section 430.63 takes precedence over Section 215.3. This is because Section 430.63 accounts for the locked-rotor current of the largest motor, ensuring that the overcurrent protection device is appropriately sized to handle both normal operating conditions and transient events. Failing to properly account for the motor's locked-rotor current can lead to nuisance tripping, equipment damage, and increased risk of electrical hazards. Therefore, it is essential to carefully consider all components of the feeder load and consult the NEC for accurate calculations and proper selection of overcurrent protection devices. It is also important to consider the specific characteristics of the overcurrent protection device, including its type and interrupting rating, to ensure that it provides adequate protection for the circuit. Let's further clarify the distinction between continuous and non-continuous loads. Continuous loads, as mentioned before, operate for 3 hours or more continuously. Examples include general lighting in commercial buildings, HVAC systems, and industrial machinery that runs for extended periods. Non-continuous loads, on the other hand, are loads that operate for less than 3 hours continuously. Examples include receptacles, intermittent lighting, and small appliances. The distinction between these two types of loads is important because the NEC requires that continuous loads be multiplied by a factor of 1.25 when calculating the feeder load. This is to account for the additional heat generated by continuous operation. Non-continuous loads do not require this adjustment. Additionally, let's explore the concept of demand factors in more detail. Demand factors are used to reduce the calculated load for non-continuous loads, such as receptacles, based on the assumption that not all loads will be in use simultaneously at their maximum capacity. Demand factors are typically expressed as a percentage and are applied to the total calculated load. The specific demand factors to be used are provided in Article 220 of the NEC and vary depending on the type of occupancy and the number of receptacles. For example, a commercial building with a large number of receptacles may have a demand factor of 50%, meaning that only 50% of the total receptacle load is considered when calculating the feeder load. Using demand factors can significantly reduce the size of the feeder conductors and overcurrent protection device required, resulting in cost savings. However, it is important to carefully consider the specific application and ensure that the demand factors used are appropriate. If the actual load exceeds the calculated load based on demand factors, the feeder conductors and overcurrent protection device may be undersized, leading to potential hazards. Furthermore, let's discuss the importance of coordination between overcurrent protection devices. Coordination refers to the selective tripping of overcurrent protection devices, such that only the device closest to the fault trips, while upstream devices remain closed. This minimizes the extent of the outage and allows the rest of the system to continue operating. Coordination is achieved by carefully selecting the characteristics of the overcurrent protection devices, such as their time current curves, so that they trip in a coordinated manner. Coordination studies can be performed to ensure that the overcurrent protection devices are properly coordinated. In addition to the technical aspects of overcurrent protection, it is also important to consider the safety implications. Electrical hazards can be deadly, and it is essential to follow all applicable safety codes and regulations when working with electrical systems. Only qualified and licensed electricians should perform electrical work. Before working on any electrical circuit, it is essential to de-energize the circuit and verify that it is de-energized using appropriate test equipment. Personal protective equipment, or PPE, such as gloves, safety glasses, and arc-rated clothing, should be worn when working on or near energized electrical equipment. Regular inspections and maintenance of electrical systems are also important to ensure their continued safe operation. Overcurrent protection devices should be inspected regularly to ensure that they are in good working condition and that the interrupting ratings are adequate. Any damaged or malfunctioning overcurrent protection devices should be replaced immediately. In conclusion, sizing the overcurrent protection device for a feeder load that includes continuous lighting, non-continuous receptacles, and motors requires careful consideration of all components of the load and adherence to the NEC requirements. Section 430.63 takes precedence over Section 215.3 in this scenario because it accounts for the locked-rotor current of the largest motor. Failing to properly account for the motor's locked-rotor current can lead to nuisance tripping, equipment damage, and increased risk of electrical hazards. It is essential to consult the NEC for accurate calculations and proper selection of overcurrent protection devices, and to follow all applicable safety codes and regulations when working with electrical systems. By following these guidelines, you can ensure the safe and reliable operation of electrical systems.